Hi guys. So today we're gonna talk about deriving mass and energy balance, deriving differential equations for how temperature of water and air and the concentration of water, vapor, molar water, varies with respect to position. Um, so we can use mass and energy balances coupled with the Lewis relation that we did earlier. So I'm gonna draw the scenario. So we would have a cooling tower. So essentially how it works is air would travel through the cooling water and the water, and they're going to travel through opposite direction, air and water. And what the temperature of water is going to be usually hot water, and when it contact with the air, some of the water vaporize and loses energy, or give energy to the air and draws energy from the hot water to vaporize, which will cool down the temperature of the water. So I'm gonna draw a scenario. Let's say imagine water temperature coming in T1 and temperature of water, okay? T water 1, T water 2, water coming out. T water 1 is 60 degree, and T water 2 is 30 degree. And then at the same time, air is going in the opposite direction. Air 1 and air coming out this way is air 2. And so we're gonna derive all of these equation, okay? So first we want to, I'm also gonna introduce something here. Let's draw a square. And so this thing is called packing. So its purpose is to maximize surface area and contact between air and vapor. It has a unit of meter square over meter cube. So, and all these are the variables that we want to define for. D, change in temperature of water with respect to dz, change in temperature of change in concentration, change with respect to position, and change in temperature of air with respect to position. So now I'm gonna show you what the packages would look like. So water would coming in this way, water in, water out. And then air would come in this way, air in, air out. And so let's just say water would have, let's do a a flow rate, a mass flow rate of water, L, and it would have a unit of kilogram over meters over meter square per second. And now we can start with the first one, change in temperature of water with respect to Z, okay? So first over onto the left side, we're gonna have change in enthalpy of water. And it's gonna be volumetric flow rate, mass flow rate times heat capacity times the packing A times A times packaging times area times dz at the end, because meter square over meter cube times meter square times meter is meter square. So that's the area that we wanted. All right. The surface area with the contact minus T water 1 minus T water 2 times dz. Or actually, I made a mistake. There's actually no dz over here because it's just the change overall of the enthalpy of water with doesn't have to be respect to z yet. And then over here we would have um heat transfer between water and water between water and it would have a formula of A packing times surface areas times temperature of air minus temperature of water times dz. And this is the one we need dz, because for surface area. And oh, I still forgot H to H, and then plus the heat loss by vaporization. So latent heat of vaporization by water, and it's gonna be AC times lambda times packing times surface area times concentration of interface minus concentration of the bulk air. So instead of writing C in that way, I'm gonna write it in terms of ideal gas law. So we have P sat. So we assume that the pressure at the interface is saturated. We know that it's saturated actually. We don't have to assume, I'm sorry. And then times RT. So that's our first equation. And then energy balance equation. And then now we're gonna just keep deriving it, okay? So here we can cancel out and AA. And we can, oh, I forgot DZ over here as well. And we can divide it both side by DZ and move mass flow rate and heat capacity to the other side. So we would have dTW over dZ is equal to H T air minus T water over L heat capacity. And wait, yeah, let me just move this over here too. Oh, and then I forgot this is heat capacity of water. Heat capacity of water, and then plus, let's move this onto the middle, plus Kc lambda over L heat capacity times P saturation of water over RT minus C. And so that's how we got our first derivation for changing differential equation and changing temperature of water with respect to position. And now we're going to move on to change in concentration with respect to position, okay? So now, um, for molar concentration, we know that for molar concentration, we know that air is also has a flow rate, volumetric flow rate, and so let's name it G, volumetric flow rate of air, which has a unit of mole. Oh, actually, volumetric flow rate of water. I'm not air. I'm sorry. Mole of hydrogen over meter square times second. And so now, um, we can have the left and the right hand side as well. So the right hand side is the C times packing AA times um concentration minus the rate of concentration of water. Change in concentration of water would be again P sat over RT minus C. And then finally times dz because we're gonna make this surface area. All right. So we know that over on the left side, the A or the area doesn't change, surface area doesn't change. And also the vol assume that the volumetric flow rate stay constant. We can rewrite this as dc divide both side by dz is equal to kc, and then we can also cancel out a over here as well. So we just have kc over g times packing times psat over rt minus c, and that's how we derive the equation for change in molar concentration. And then last, we're gonna work on change in temperature of air with respect to um, position. So same thing for earlier, we can have change in enthalpy of air, and then we would have heat transfer, and then we would have on the right hand side, we would also have latent heat vaporization that's released when water vaporize. So first on the left hand side, we would have derivative of rho times area times volumetric flow rate times temperature of air times heat capacity of air plus lambda over density times concentration. And so that's for the left hand side. And then for the right hand side, we would have packing times surface areas times um heat transfer coefficient times temperature of air minus temperature of water times dz. And then over here, down here, we would have kc times lambda times packing times concentration at the surface area minus concentration of bulk air times dz. Now we're gonna rewrite this equation, okay? We're gonna simplify it. So we know that over here, these are all constant except T air and concentration. So we're gonna take it out of the bracket. So we'd have rho A G's times DT air times C P air, capacity of air, lambda over rho times DC. And then we can open the bracket. Oh, and then we can also cancel rho over here. So we would just have lambda AG times DC. All right, so let's continue. And then we would let's rewrite this over on the left-hand side, and we can also cancel out some variables. We can cancel out A over here. Oh, I'm not sure why this one's under here. Rho AG. And then we can cancel out area. And so we would only have AHT air minus T water dz plus Kc lambda A P sat RT minus C dz. And then we're gonna divide dz on both sides, okay? P Cp air G times dt air dz plus lambda G dc dz is equal to AHT air minus TW plus Kc lambda A P sat RT minus C. And so earlier when we derived dc over dz, we know that it's equal to Kca over G. P sat RT minus C. So when you times it with lambda and G, we're gonna cancel out lambda and G, and then we can have lambda, which is exactly what we have here. So we can cancel out these two variables, which left us with rho C, K capacity of air times G dt air over dz is equal to AHT air minus T water. And then we can move everything else to the other side. dt air dz is equal to packing times heat transfer coefficient times T air minus T water over rho C heat capacity of air times. So we came up with the last equation. And then now we're gonna move on to Excel, okay? So now that we've derived the differential equations for water, air temperature, and molar concentration of water. Thank you for listening. Hi guys. So yesterday we talked about earlier in the question one, we derived three differential equations for how temperature of water and air and molar concentration of water changes. So today we're gonna do a simulation in Excel to show how that would change the temperature of water, air, and the molar concentration w- based on position. So first we're gonna define some value, okay? So we're gonna have T water in, oops. First, we're gonna have T air in, and then T water in, and then T water out, and then we have saturation concentration. So first, T air in is um 30 degree, which when we convert it to Kelvin is gonna be 303.15, and then T water is 50 degrees. So it's going to be 323.15. And then T water out is 30. And then we're going to have same thing. And then to calculate concentration saturation, we're going to use um Antonin, Antonin equation. Okay. So we're going to have 10 to the raised to the power of A. I'm going to write down the Antonin down here, actually. Write it down here. A, B, and C. So A is 8 point, so A is 8.07131, and then B is 1730.63, and then C is 233.428. And then we do that. So to calculate C saturation, um we're gonna take into an equation, okay? So we're gonna do 10 raised to the power of A minus um B divided by temperature of air in plus uh oh, and then we have to make sure that we use it um Celsius degree, okay? Plus C, okay? So that's our end-to-end equation. And then we're gonna divide it by, oh, and then we're gonna convert the unit to um Pascal. So we're gonna divide it, times it by 101,325, and then divide it by 760. All right, and then we're gonna also divide it, all of them by by our R constant, which I'm actually gonna define down here. R constant, say R constant is 8.314. So we're gonna do that. Okay, let's copy times R constant times time T water in. All right, perfect. And then let's see, we still have a couple more variables to define. So we can have L. So we also need to define what's the concentration of air when it first went in there. So we're gonna take LC saturation times it with zero point 0.1 because the air relative humidity is 10% of inlet air. All right, and then we're gonna define L equal to over here, let's see, 10. And then we're gonna define G is equal to uh G is equal to 5. And then we need the relative humidity, which is zero point 0.1. And then we need density of air. Let's say rho air. Density of air is equal to, all right, density of air is equal to saturation pressure times times we can have take the saturation pressure times it with the molar mass of air 0.029, and then we're gonna divide it by R times T air in. Okay. Now that we have the row of air, we have some more variables to define. Okay. So we have um Kc. We need to define Kc. So Kc is equal to H divided by, so H is our heat transfer coefficient. Just gonna define H down here first. So H is equal to 50. And then A is equal to 100. And now Kc, Kc is equal to H divided by rho air. Oh, I forgot another variables. We have to define heat capacity of water and heat capacity of air. So heat capacity of air is 1,000 joules over kilograms Kelvin, and then water is 4185. Okay, so now Kc is H, or the heat transfer coefficient, divided by density of air, just this, times heat capacity of air. And then you just put it in a bracket. Got this. Perfect. And then let's see. We need to define, we already have end-to-end coefficients, and then we just need to define lambda, R and lambda. So lambda in this case is 40650. Okay. And then after lambda, we need you need dz, and then the height of the height of the thing. And so let's just say it's 10 for now, and dz is 0.01, and then we're gonna need to define at the end what did we get for the T water in calculated from the chart that we're gonna do later, and then the error, which is the square difference, right? So now moving on here, we can start with 0, and then we're gonna create a series. Okay, so it's gonna be um home. Let me just expand this because I don't need that window anymore. So it's gonna be fill with series, column, stop value is 1,000, and then our z would just simply be dz over here times with this series, and then don't forget to lock it. Right, I'm just gonna drag it down. All right. So first we need to define C, which is concentration, and then T water in, T water, T air. So at 0, at Z equal to 0, it's the inlet, okay? T air, and then C diff, and then P sat of water. C difference concentration, and then DC DZ, D DT water DZ, and then DT air over DZ. So for our concentration, it's gonna be right. So for concentration, we're just gonna copy it from here. C air in, and then T water, same thing. So at this point, water is coming out, and then air is coming in because they're traveling in a counter direction. Oops. 3. And then T air is just T air in, and then P sat water. I'm just gonna copy the end-to-end equation, okay? So let's see, P sat. Hold on. Yeah, I'm just gonna copy this equation over here. And then we're gonna replace the temperature with this. And then don't forget about the converting it to Kelvin too. And then we're gonna also lock these as well, just in case. Yeah. Mhm. So after we got the saturation of water, we can move on to C diff. All right. So the concentration difference is just um, P sat of water divided by R times T of air. Um, then put them in parentheses. And then minus this. Yep. And then we're gonna do DZ and DC and DZ. And also don't forget to lock this too. All right. And then for DC and DZ, we're gonna based on the equations that we derived on the first part of this homework. So I'm gonna go back to it. So DZ is equal to let's see, KC is equal to KC times A divided by G divided by G times P sat times P sat times P sat over here. Mine divided by RT. So R times T air. And then oh, and then don't forget to put this in parentheses as well. And then um, minus C. All right, so we've gotten DC, or I can just simply replace this entire thing um with C diff because we already got C diff over here. And then DT water DZ is equal to, let's see, for T water is equal to H H times H times is equal to H times T air minus T water divided by L times heat capacity of water. And then let's put them all in a bracket. And then plus um, Kc lambda, it's Kc times lambda, Kc lambda divided by L times G times G, and then times C diff. Okay, so yeah, let's see. Let's double check this. Okay. Kc lambda C diff times C diff, C diff divided by L, heat capacity of water. Okay. Sorry guys, I made a mistake over here. So this is supposed to be B13, and then I also missed the packing as well. So it's supposed to be case, it's supposed to be H times A packing times difference in the temperature, blah blah blah. So let's retry this. Right, looks more correct now. It looks more correct now. So and then we can move on to DT air DZ. So let's see. DT air is equal to packing times H times the difference in the temperature, T air minus T water, all divided by rho, rho air, times heat capacity of air times G. And then we don't forget to log these two. All right, and then I'm also gonna lock this answer over here. All right, and then same for here. Just make sure I lock all of these values. And then, so down here, we're gonna do this H2 plus dc dz times dz, and then lock it. Okay. And then for T water, T air, it's going to be a similar thing. So T water, initial T water time plus the change in T water with respect to time with this position times change in position. Okay. All right. And then T air is just um same thing. And then I'm just gonna copy these down here. All right. So now that we drag all these down, let me just double check real quick to make sure nothing's wrong. And then I'm just gonna drag each of these column down. Yeah, over here. Oops. Oopsie. Oops. Let's redo this. Okay. And then same thing for air, temperature of air. Then watt saturation pressure. And then seated. All right. And then just DT water. and then dt air. All right. So now this number looks very big in difference, but